Here is the promised example 5 from chapter 10. You'll notice this problem is very similar to a problem that we did in chapter 9, almost the same. I've just tweaked the data just a tiny bit. So just to remind you, we have this course in statistics for business majors, and the college administration is hoping that the course will improve scores on a certain standardized test by at least 10 percentage points. So to test that, we did a pilot on 20 freshman business majors. We had them take the standardized test and record their scores before they had the course. And then we had them take and record their scores after they had taken the course. And the goal is to see an average improvement of 10 percentage points or more. And so we're asked to actually find a 99% confidence interval for the difference in means, and then also do a hypothesis test as well. I thought it would be good to practice both. So there's a slight issue that comes up here. It's not really a big deal, but it comes up to which one should we label? Should we label this sort of population 1, population 2, thinking of all the students? So this is a sample, right, of all students taking the pretest. And this is sort of a sample of all students taking the post-test. And so in most of the problems, it doesn't really matter how you label. And I guess it doesn't really here either in some sense. But if you recall, let me scroll up and find our formula. Our formula for confidence interval uses x1 minus x2. And I like that to be positive. I'm thinking about improvement being positive. How much did it actually improve? And so think about it. This difference is only going to be positive if this number is bigger than this number. And so with that in my mind, and I'm thinking about which one to label which, I'm actually going to label the post-test as the first sort of data and the pre-test as the second. That way, when I write down x1 bar minus x2 bar, I'm saying this score minus that score. The first score, I get a negative difference, right? This student actually went down in a point, but overall, I'm hoping that average will be positive. So if that doesn't make any sense, stick with me and go ahead and finish the problem, and I think you'll see why it's not a big deal. You'll just get something that's negative what I got if you go the other way, and you just have to interpret it. So here we go. So what are the pre-tests? So let's see. The x1 bar averages. We'll start with the post-test. x1 bar is going to be 80.0526. x2 bar is going to be 66.95. The sample standard deviation for x1 is 10.0746. The sample standard deviation for x2 is 10.6449. Of course, the sample size for the post-tests is N1 equals 19. We lost a student, didn't take the post-test. The sample size for the pre-test was actually 20. So that's sort of the initial statistics that we'll need to get. You could type this stuff into Excel if you wanted to. We're interested in doing a 99% confidence interval, so let's kind of deal with that. So I want C to be 0.99. I need my degrees of freedom. I know those are going to be what? The smallest of either 19 minus 1 or 20 minus 1. 19 minus 1 is 18. That's the small one. And I want 99% of the area in the middle between T star and minus T star. Your goal is to find T star. So I'm going to use the app for that. I think I've got it already typed in. Yeah. So I put in my degrees of freedom is 18. And let me delete this box and it'll still run it for me. I want my area to be 0.99 and it'll spit out. When you type in the area of 0.99, it'll tell you the blue is the T-score, even though it's called X. So let's just round to 2.88 and call that good. So T star, the critical value is 2.88. Okay, so we've got that. And actually at this point, we've got everything we need to pull off a 99% confidence interval. So let me draw a line and we'll kind of get this cleaned up and then we'll go ahead and knock it out. All right, so let's do it. So pull out your formula. If you don't have it in front of you, I would encourage you to pull it out and then watch how this goes. So I'm going to take x1 bar minus x2 bar, so 80.0526 minus 66.95. Okay, then I'm going to say plus or minus the square root of, and then I take my first sample standard deviation, 10.0746. I square that and I divide by my first population size of 19. Then I take the other one and I do 10.6449 and I square it and I divide by 20, and that's it. You have to compute that, and when you do, you'll get 13.1026 plus or minus 9.55. I'll knock off the 003. There's a little bit more if you didn't round everything. So this is a problem where it's probably good to actually add or subtract the 9.5 to everything. When you do, you'll get an interval of 3.55 all the way out to 22.65. And so at a 99% confidence level, all we can say is that the true mean improvement, the true difference in means here, when you take the post-test scores minus the pre-test scores, is somewhere between 3.5 percentage points and 22 percentage points. So it does not at all need to be 10 or more. It could be 10 or more. It could be way less than 10. And so that's all we can say at the 99% confidence level. So this is a 99% confidence interval. And so that confidence interval doesn't make us feel real good about knowing that our average is above 10. Yeah, the average here is 13, but there's a lot of error there, so we really can't say. I think it would be good for us to do the hypothesis test version of this as well. So let's actually write that out. So what are we saying? The null hypothesis is nothing's happening. These scores are not actually improving. So M2 minus M1 is less than or equal to 10. And the alternative hypothesis is actually no, M2 minus M1 is greater than or equal to 10. All right, and let me make sure, yeah. So that's the setup. To compute this, you'd want to go ahead and compute the t-statistic, and you would get 13.1026 minus 10, and you would divide by the square root of the same thing we did before, 10.00746 squared over 19 plus 10.6449 squared over 20. And let me just bring that over. And yeah, we'll compute this, and you get 0.935. Yeah, that's good enough. Okay, so you don't have to use an app to predict this. You can say, well, this thing, the t-distribution is not that different from normal. I'm less than 1 standard deviation from the mean. I'm going to have a very large tail. And so I'm going to have a large p-value. And that's true. Let's actually compute it. You want the probability that t with, what do we say, the degrees of freedom were? I think 18, right? Yeah. 18 degrees of freedom is greater than or equal to 0.935. This probability, it turns out, is about 0.18108. And that's very similar to what we got last time with the matched pairs. And so the point is you would fail to reject the null hypothesis. This data is not providing evidence that the actual exam scores are improving by the 10 percentage points requested. And you can see that back here, the overlap between this large p-value and the fail to reject actually can be seen here, because your goal that you wanted to be at the null hypothesis, the null hypothesis value is mu2 minus mu1 actually equals 10. We can make this equals 10 if we want here. This actually falls in there. So when your null hypothesis value falls in there, then it's to be expected, and somehow then that you don't reject the null hypothesis. So I had put a less than or equal to 10 before, and then I used the 10. The point is you always pick the most extreme, so you would want to work with equals 10 here. So that's problem 5. The only difference is that most of the null hypothesis examples we've done is mu1 equals mu2, and this one we had a little bit different null hypothesis, but you can make it work, no problem at all.